Hey there. In this video, we're going to be looking at ionization energy and some associated periodic trends. Let's get into it. First things first, let's start with a definition. Ionization energy is the energy required to remove an electron from a gaseous atom, or an atom in the gas phase. And here is the general equation for that. As you can see, we have an atom, and an electron is being removed from the atom, producing a positive ion. All right? And if you ever forget what ionization energy refers to, you can kind of derive it from the name itself. The term ion here kind of explains this entire thing. You remove the electron and you produce an ion from the previously neutral atom. All right, so if you ever forget what ionization energy means, remember the term ion and that removing the electron produces an ion. All right, so the next part that's important to know is about the electrons being removed. So here is an example in sodium. And what happens is when I refer to ionization energy, the electrons that are being removed, that are more likely to be removed, are the ones that are the furthest from the nucleus, that are the least attached. They're going to be the most vulnerable electrons, and they're typically the outermost valence electrons. So in sodium, in this instance, the first ionization energy is going to be the removal of this electron. If I suggest a second ionization energy, it's going to be one of the other electrons in this second shell here. And then the third one's going to be another one again. So that's kind of how it works. It's going to go in order from the outermost to innermost. So the outermost is going to have a much lower energy threshold to take out the electron than the innermost, because the innermost is very close to the nucleus, right? And it's going to require a lot of energy to break that positive and negative bond, the attraction there, not the bond, yeah. So one concept that's very important to note when it comes to ionization energy, and we'll look at this when we come to the trends in the periodic table, is the concept of effective nuclear charge. And really, this is a very important concept in AP chemistry. And really what it is that it's just a fancy way of saying that positive charge, the positive charge that is experienced by a valence electron, right? That's all it is. It's just a really fancy way of saying this. So the higher the effective nuclear energy, the more positive force the more positive force is exerted on the electron, and the more attraction there is. So that's going to mean that there's going to be a higher ionization energy. It's going to require more energy to take apart, right? However, if the effective nuclear charge is very low, right, it's going to be a low ionization energy because, well, there isn't as much attraction between the protons and the electrons that hold the electrons in the atom, which makes it easier to take away. All right, so hopefully those concepts made sense. And now let's look at some trends. First trend is that from left to right across a period, so from left to right across one of these horizontal columns, ionization energy will increase. All right, so ionization energy. And that is from this side of the table to this side of the table within the same period. Now, when it comes to understanding periodic trends, it's really important that you don't memorize random directions. You should kind of have an understanding of what's going on, because if you just memorize these directions, you may slip up on a test, you may get some thinking questions wrong. You have to have an intuitive understanding as to why ionization energy would increase from left to right. And here is an explanation. So this example uses lithium and fluorine. All right, so from this trend, it should be said that fluorine would have a higher ionization energy because it is more towards the right, right? And here's why. Lithium, right, this is the Bohr-Rutherford diagram for lithium, and this is the Bohr-Rutherford diagram for fluorine. Now, what's similar about both of these elements? Let's establish that. What is similar? They're similar because they only have two principal quantum levels, right? There's only two shells in both of these elements that are filled with electrons, right? Lithium has 1 electron here, and fluorine has 7 on the outside. All right, and what's significant about this is that all elements within the same period have the same number of shells, right? So the distance between the furthest electron and the nucleus will remain constant across the period because there's the same number of shells. You're just adding electrons for each new atom. What's also significant is that across a period, you're actually adding protons, right? That's what these numbers are. You're adding protons. So if you combine both of those facts together, you know that across a period, the distance from the furthest electron and the nucleus remains somewhat constant. And you also know that across a period, the number of protons increases. That means that the effective nuclear charge, so the effective nuclear charge is going up, right? That means that the effective nuclear charge is going up because the attraction experienced by these electrons just goes up as there's more protons. The electrons aren't getting further away in the period. They're just being added to the same shell, while the protons are slowly getting stronger. So that's what this protons make the positive force in the nucleus slowly become stronger, which increases the effective nuclear charge, which then will increase the ionization energy. All right, so that is kind of how that works, and hopefully that made sense. Just think of it as maximizing the effective nuclear charge as you go across. All right, the second trend is that ionization energy tends to increase as you go up a group. A group is a vertical column, one of these things, and that was a very bad drawing there. But this one is a bit more easy to conceptualize. If I were to ask you the differences between lithium's Bohr-Leffler diagram and sodium's Bohr-Leffler diagram, and please don't see that, it's pretty obvious. It's that, okay, sodium's bigger, there's more shells, there's more valence shells, and that exactly is the reason why sodium is going to have a lower, right? Sodium is going to have a lower ionization energy because it has more shells. The electron is further away, right? And when something is further away, the attraction weakens. So the effective nuclear charge, I'll just abbreviate it, effective NC, experienced by this electron is going to be lower because it's further away. There's more shells that are separating it. There's also a phenomenon called electron shielding, where the negative forces of these electrons repel and just push this electron further away. And since the effective nuclear charge is lower, the ionization energy, right, is also lower, right? Because it's easier to take away now. There's less force from the nucleus holding it together. We can pry this thing off fairly easily, right? Now compared to this one, now although there's only 3 protons, the fact of the matter is the electrons are very close to the 3 protons. Right? They're very, very close. So there is a strong force of attraction there. The effective nuclear charge on this electron is very high, which is going to give it a high a high ionization energy, right? And that is the reason for that general trend. So to summarize, ionization energy increases as you go up a group, and it increases as you go from left to right across a period. And it's really important to know the term of effective nuclear charge. That's a very important term for AP chemistry, and generally it will help you explain the trends you see in ionization energies. All right, so hopefully you enjoyed the video. If you did, click the like button, consider subscribing to the channel, and I hope to see you guys soon.